All right, so tonight I'm going to talk about the product rule and the quotient rule. So the key idea is, suppose I have a function f. Suppose I have a function f of x and I have another function g of x. Then the key thing here is that if you multiply the functions and take the derivative, you do not get the product of their derivatives. And if you take the quotient of the functions and you take the derivative, you don't get the quotient of the derivatives. So probably the easiest way to see that this is the case is, the easiest way to see this is the case is suppose I give you the function f of x equals x squared and g of x equals x. All right? Then f of x times g of x is equal to x cubed, and the derivative of x cubed is 3x squared. Now notice f prime is 2x and g prime is 1. So this is not equal to f prime of x times g prime of x, which is just equal to 2x. Similarly, f of x over g of x equals x squared over x is 1, or as x to the first, and the derivative of x is 1. This is not equal to f prime over g prime, which is equal to 2x over 1, which is 2x. So something more complicated happens when you take derivatives of products and quotients of functions. And there are slides up on Blackboard that sort of derive this, but the important thing is here's the product rule. The product rule says that the derivative of the product of two functions is the derivative of the first function times the second function plus the first function times the second function. So using our example up here, I had f was x squared, so f prime was 2x. I had g was x, so g prime was 1. And so then if I plug that into here, I'm going to get 2x times x plus x squared times 1, which is in fact 3x squared, which is the derivative with respect to x of x cubed, which is what f times g is. So the product rule works. Similarly, the quotient rule says that if I want to take the derivative of f over g, I'm going to get f prime times g minus g prime times f all over g squared. So again, I had f was x squared, g was x, f prime is 2x, g prime is 1. So if I fill all this out, I'm going to get 2x times x minus 1 times x squared all over g is x squared. Why do I feel like I'm missing something up here? No, actually, this is totally right. What's wrong is no, actually, no, I did it totally right. So this is 2x squared minus x squared over x squared. which is x squared over x squared, which is 1, which is, in fact, the derivative with respect to x of x squared over x. So we can use the product and the quotient rule to take derivatives of very complicated things. Now, it's not always strictly necessary that we use the product rule, so let me give you an example. Suppose I have the function x minus 5 times x plus 2. I can think of this in terms of the product rule, where I think of this as f and this is g. So if this is y, then y prime is going to be f prime times g plus g prime times f. Now, f prime here is 1, and g prime here is also 1. So what you're going to get out of this is x plus 2 times 1 plus x minus 5 times 1. And that's equal to 2x minus 3. Now, another way I could have gotten that is if I took this expression and I multiplied everything out. And if I multiplied everything out, you'd get x squared minus 5x plus 2x minus 10, which is x squared minus 3x minus 10. So y prime is, in fact, 2x minus 3. It's just, that's all there is to it. And the thing with the product rule is sometimes you can get away with actually multiplying the expression out beforehand, and then you end up not needing the product rule at all, like is what happened there. The quotient rule, there's usually no way around it. So let's take f of x is 3x minus 1 over x plus 5. I don't want to call it f because that's confusing. Let's call it h of x. So in this formulation, I'll think of f as 3x minus 1, and I'll think of g as x plus 5. And so now if I take derivatives here, I'm going to get that f prime is 3 and g prime is 1. So using the quotient rule here says h prime of x is f prime g minus g prime f all over g squared. And that is 3 times x plus 5 minus 1 times 3x minus 1 all over x plus 5 quantity squared. So then that becomes 3x plus 15 minus 3x plus 1 over x plus 5 quantity squared, and the 3x's cancel, and so you get 16 over x plus 5 quantity squared. So we can also combine this with the exponential and logarithmic functions from the previous section. So let's say that my function h of x is actually x squared times e to the x. Then I think of x squared as, say, f, and I think of e to the x as g. So then when I say that h prime of x is f prime times g plus g prime times f, then I'm going to take advantage of the fact that I know that f prime is 2x, and I know that g prime is e to the x, so that this just works out to 2x times e to the x plus x squared times e to the x, which is sort of weird, this final answer. But you get answers like this when you take derivatives of like powers of x times e to the x. You get this sort of rolling polynomial thing that's going on. All right. So let's try one more. Let's try h of x equals the natural logarithm of x over x minus 4. So we'll think of this as f over g. F prime is 1 over x, and g prime is 1. So this should not be very difficult. When I find h prime of x, it's going to be f prime g minus g prime f all over g squared. And so I can sort of glumly plug all these numbers in. The derivative of f of x is 1 over x. So this is 1 over x times x minus 4 minus 1 times the natural logarithm of x all over x minus 4 quantity squared. Because this is f prime g minus g prime f all over g squared. And so this works out to something like 1 over x times x minus 4 minus the natural log of x over x minus 4 quantity squared. So that's it. All right. So I am going to give you a handout, which should be on Blackboard by now. It's not there yet. I'll give you a handout with some more of these practice problems on it, so you can go over them, and then I will go over the solutions to the handout in a video. All right.